The Gatling gun, patented by Richard Gatling in 1862, was not a true machine gun. It required a human operator to turn a hand crank, rotating multiple barrels through a firing cycle. The system could theoretically achieve 200 rounds per minute. In practice, reality proved far more complicated. Black powder fouling clogged the mechanism within minutes of sustained fire. Brass cartridge cases expanded from heat, jamming during extraction. The rotating barrels overheated, despite the multi-barrel design's attempt to distribute thermal load. Crews discovered that theoretical rates meant nothing when the gun seized after the first 100 rounds. The weapon weighed over 170 pounds without its wheeled carriage. Moving it required a dedicated crew of 4 to 6 men. Ammunition supply became a logistical nightmare. Each engagement consumed thousands of rounds, far exceeding what infantry could practically carry or resupply under fire. Competing designs emerged, each claiming superiority. The Gardner gun, introduced in 1874, used 2 barrels instead of Gatling's rotating cluster. The Nordenfeldt gun, patented in 1873, featured multiple barrels fired by a single lever mechanism. All shared the same fatal dependency on human muscle power. Colonial wars in Africa and Asia provided brutal field testing. British forces at the Battle of Ulundi in 1879 used Gatlings against Zulu warriors. The guns performed adequately in brief engagements. Extended battles revealed crew exhaustion as the limiting factor. Men could not sustain cranking speeds for more than a few minutes. Suppressive fire remained physically impossible. The fundamental problem was obvious. Every hand-cranked weapon required external power. Human endurance imposed hard limits on sustained automatic fire. Gun designers could add more barrels, improve extraction mechanisms, or refine ammunition feeding systems. None of these innovations addressed the core limitation. The soldier's arm could only turn the crank so fast, for so long. But one inventor in London was about to eliminate the hand crank entirely, and in doing so, would change warfare forever. The Maxim gun, invented by Hiram Maxim in 1884, was the first truly automatic weapon. It harnessed the gun's own recoil energy to cycle the action, reload, and fire again without human intervention. The cyclic rate reached 600 rounds per minute, no hand crank required. Maxim's toggle lock mechanism was mechanically brilliant. Recoil force drove the barrel and bolt backward, unlocking at a precise moment to extract the spent cartridge. A belt fed fresh ammunition into the chamber. The cycle repeated as long as the trigger remained pressed and ammunition lasted. The design worked, but it brought catastrophic new problems. Water cooling was mandatory. The barrel generated enormous heat during sustained fire. Maxim surrounded it with a steel jacket filled with water, adding over 50 pounds when full. The complete system weighed between 60 and 100 pounds depending on configuration. Tripod, ammunition boxes, and water supply required 4 to 6 men to move and operate. Early British trials revealed the system's volatility. Water inside the cooling jacket boiled during extended firing sessions. Steam vented from overflow tubes. In some cases, pressure built faster than vents could release it. Cook-offs occurred when cartridges ignited from residual heat rather than firing pinstrikes. The toggle mechanism, stressed by continuous operation, fractured under sustained use. The Russo-Japanese War of 1904 to 1905 provided the first large-scale battlefield test. Both sides deployed Maxim guns extensively. Winter conditions in Manchuria exposed a fatal weakness. Water in the cooling jackets froze solid. Guns became useless chunks of ice and steel. Crews attempted to thaw them with fires, risking ammunition cook-offs. The weapon designed to dominate modern warfare sat silent in freezing trenches. World War I proved the Maxim concept despite its flaws. German MG-08 and British Vickers guns, both Maxim derivatives, defined trench warfare. Crews fired tens of thousands of rounds in single engagements. Water evaporated constantly from the jackets. Official procedure called for regular refilling from canteens. Desperate circumstances led to unofficial solutions. Soldiers urinated into the cooling jackets during extended battles. It was sterile, it was available, and it kept the guns firing. The Maxim proved automatic fire was possible, but its immobility turned machine gunners into sitting targets, a problem that would spawn an entirely new category of weapon. The Lewis gun, introduced in 1911 by American designer Isaac Lewis, eliminated the water cooling jacket entirely. Air cooling replaced it. A distinctive aluminum shroud surrounded the barrel, using the gun's own muzzle blast to draw cooling air through the jacket. The system worked. It reduced weight to a manageable 28 pounds, but it created a new problem that would kill thousands of gunners. The 47-round Pan magazine sat on top of the receiver. In prone position, the massive circular magazine protruded above the soldier's profile. Enemy riflemen spotted Lewis gunners instantly. The distinctive silhouette became a priority target. Worse, the Pan mechanism jammed constantly when dirt entered the spring-loaded system. Replacing an empty magazine under fire required exposing yourself to reload a clumsy, fragile component. Many gunners never completed the process. The French Chauchet, rushed into production in 1915, became the most despised firearm of World War I. Long recoil operation in 8mm Liebel caliber created violent reciprocating motion. The Half Moon magazine featured open sides to show remaining ammunition. Mud, dirt, and trench debris poured directly into the feed mechanism. Extraction failures were constant. The bipod collapsed under normal use. Ergonomics were punishing. The buttstock angle created brutal recoil. French troops tolerated it from necessity. American forces, issued the Chauchet in 1918, actively abandoned them on battlefields. Soldiers threw away their assigned weapons to carry captured German MG 0815s. The rejection was total and unprecedented. John Browning's automatic rifle appeared in 1918, offering superior reliability. The bar fired 36 from a 20-round box magazine. It worked. But the limited capacity meant frequent reloads in combat. No quick-change barrel existed. Sustained fire overheated the barrel beyond safe operating temperatures. Gunners had to choose between tactical needs and mechanical limits. Interwar years saw desperate experimentation. The Czech ZBVZ-26 achieved modest success with top-mounted magazines and quick barrel changes. The Japanese Type 11 featured a hopper-fed system that jammed in any field conditions. Each design pursued the same impossible goal: sustained automatic fire from a weapon one man could carry and operate alone. The mathematics were brutal. Lightweight meant limited ammunition capacity. Limited capacity demanded frequent reloads under fire. Frequent reloads in combat meant exposed gunners. Exposed gunners meant casualties. No amount of engineering could solve this equation. While armies struggled to make machine guns portable, another approach was emerging: make the bullets smaller and the gun even lighter. The MP-18, designed by Hugo Schmeisser and introduced in 1918, became the first mass-produced submachine gun. Simple blowback operation in 9mm parabellum. A 32-round snail drum magazine borrowed from the Luger pistol. German stormtroopers used it in the final offensives of World War I. The weapon worked for close-quarters trench fighting. It revealed a fundamental trade-off that would define the category forever. Pistol-caliber ammunition meant effective range under 200 meters. Beyond that distance, the rounds lost energy and accuracy dramatically. But the simplified mechanism and lighter weight enabled a new kind of warfare: room-to-room combat, trench clearing, urban fighting. The MP-18 filled a niche nobody knew existed. John Thompson's M1921 pursued the same concept with American ambition. The trench broom featured an overcomplicated Blish lock system that added weight and cost without improving performance. The weapon weighed 10.8 pounds empty. Production cost reached $200 per unit, equivalent to over $3,000 in modern currency. Police departments could not afford it. The military rejected it as unnecessary. Prohibition-era mythology surrounded the Thompson. Gangster iconography suggested widespread criminal use. Reality contradicted the legend. The weapon was too expensive for most criminals and too heavy for concealment. Commercial sales failed catastrophically. Only World War II desperation brought the Thompson into military service at scale. The war forced brutal simplification. Britain produced the Sten gun for $11 per unit. Stamped steel construction, crude welding, a side-mounted magazine that fell out during movement. The MP40 replaced Germany's expensive MP38 with cheaper manufacturing methods. Function mattered more than refinement. The Sten's economy came with lethal consequences. Dropped weapons discharged accidentally, killing soldiers in training and combat. The side magazine was vulnerable to damage and dislodgement. Crude construction meant accuracy degraded beyond 50 yards. Troops used them because nothing else was available, not because they were effective. Open terrain rendered submachine guns nearly useless. The caliber limitation became obvious in North Africa, the Eastern Front, and Pacific Island combat. Post-war doctrine struggled with their role: close-quarter specialist weapon or general-issue firearm. The debate continued for decades without resolution. As submachine guns found their limited niche, the question remained, what about a machine gun that could do everything? The MG42, introduced by Germany in 1942, achieved what engineers thought impossible: a cyclic rate of 1,200 rounds per minute, roller-delayed blowback operation. Quick change barrel system requiring 5 seconds. The weapon redefined suppressive fire. It also created logistical nightmares that crippled German infantry units. The astronomical fire rate became its own worst enemy. 1 second of sustained fire consumed 20 cartridges. A standard 250-round belt lasted 12.5 seconds. Hitler's buzzsaw sound provided devastating psychological effect on Allied troops. The sound also meant German units burned through their entire ammunition supply in minutes rather than hours. Barrel changes became the critical failure point. The extreme cyclic rate required fresh barrels every 150 to 250 rounds. Combat units carried 3 to 5 spare barrels per gun. Extended engagements exhausted the supply. Gunners ran out of barrels before they ran out of ammunition. A machine gun with ammunition but no functional barrel was an expensive paperweight. The M60, adopted by the United States in 1957, attempted to learn from German innovations. Gas-operated mechanism. Belt-fed 7.62mm NATO. The design looked promising on paper. Production models revealed catastrophic flaws. The bipod attached directly to the barrel. Changing a hot barrel meant losing your support system and burning your hands. The gas system fouled rapidly. The feed cover latch broke constantly. These were not minor inconveniences. They were combat-critical failures. Vietnam exposed every weakness. Humid jungle conditions caused chronic jamming. Spare parts supply chains collapsed in remote fire bases. Desperate gunners performed unauthorized field modifications, voiding any warranty or support. The weapon designed to dominate modern warfare became a maintenance burden. The Belgian FN MAG, meanwhile, achieved what American engineers could not: reliable operation in adverse conditions. Over 80 countries adopted it while the M60 struggled. The lesson was clear: reliable engineering mattered more than innovative features or cost-cutting measures. The general purpose concept itself proved fundamentally flawed. One weapon for all roles meant compromises everywhere. Too heavy for assault, too light for sustained defensive fire. No single gun could truly replace specialized weapons. By the 1980s, a new philosophy emerged. Maybe the squad didn't need a general-purpose machine gun, but a specialized automatic rifle. The RPK, adopted by the Soviet Union in 1961, took the simplest possible approach. Take an AKM rifle, add a longer barrel and a bipod. Issue a 40-round magazine instead of 30. The concept worked because it eliminated logistical complexity. Every part shared commonality with standard infantry rifles. Ammunition was identical, training was minimal, but tactical effectiveness suffered dramatically. 40 rounds provided insufficient ammunition for sustained suppressive fire. Soldiers burned through magazines in seconds during contact. No quick-change barrel existed. The weapon overheated after 150 to 250 rounds of continuous fire. Gunners faced the same choice their predecessors did: cease fire and let the barrel cool, or continue firing and risk catastrophic failure. The M249 Squad automatic weapon, adopted in 1984, promised to solve these limitations. American forces acquired the Belgian Minimi design, belt-fed operation, optional magazine compatibility, 5.56mm NATO standardization across the squad. The weapon finally gave infantry units sustained automatic fire at the squad level. Early production models revealed familiar problems. Jamming occurred frequently in field conditions. The dual feed system, designed to accept both belts and magazines, meant magazine feeding rarely functioned reliably. Gunners learned to ignore the feature entirely. Weight remained punishing. At 17 pounds empty, plus ammunition and spare barrels, automatic riflemen carried twice the load of standard infantry. Mobility suffered accordingly. The caliber debate erupted immediately. 5.56mm rounds lacked effective range beyond 300 meters. Penetration against cover proved inadequate. Taliban fighters in Afghanistan learned to engage beyond M249 effective range, negating its firepower advantage. Arguments over intermediate cartridges versus full-power rounds echoed the same debates from the 1950s. Doctrine promised maneuver warfare. Reality produced static defensive positions. Squad automatic weapons, designed to enable movement and fire, became suppressive platforms for stationary troops. The cycle repeated. New technology failed to overcome fundamental tactical constraints. Sustained automatic fire still required stable firing positions, regardless of weapon design or ammunition type. As squad automatic weapons found their footing, engineers began asking, what if we could make belt-fed firepower even more compact? The M240L, introduced in 2010, represented the materials science revolution. Titanium receivers replaced steel. Advanced polymer components reduced weight without sacrificing structural integrity. Stellite alloys in the barrel assembly provided heat resistance at lower mass. The result saved 5.5 pounds compared to the standard M240B. Soldiers noticed the difference. Engineers had finally overcome weight through chemistry and metallurgy. Bullpup configurations promised compact firepower. The EM2, the F2000, and various experimental platforms attempted to maintain full barrel length while reducing overall dimensions. The concept failed repeatedly. Ejection port placement proved unsolvable for left-handed shooters. Trigger linkages introduced mechanical slop. Ergonomics suffered catastrophically. Balance felt wrong. Soldiers rejected them universally. Dual feed systems from FN Herstal offered tactical flexibility. Gunners could instantly switch between ball ammunition, tracers, and armor-piercing rounds. Two separate belt feeds attached to the weapon. The concept worked mechanically. It added complexity. More moving parts meant more potential failures. Field maintenance became more demanding. Most units ignored the secondary feed entirely. Smart ammunition represented the cutting edge. Programmable airburst rounds, guided projectiles, ballistic computers calculating trajectory in real time. The technology functioned as advertised. Costs made it prohibitive. A single guided round cost more than 1,000 conventional bullets. The fundamental role of machine guns was suppressive fire through volume. Expensive ammunition contradicted that doctrine entirely. Optics integration followed naturally. Thermal sights, laser rangefinders, digital ballistic calculators. Each edition improved first-round accuracy. Each edition also introduced new failure points. Batteries died in extended operations. Electronics failed in extreme temperatures. Water intrusion destroyed circuitry. The most sophisticated weapon became useless when technology failed. Physics imposed final limits. Lightweight materials reduced the gun's weight. Ammunition still had mass. Belt-fed mechanisms still required structure. No material science breakthrough could eliminate these fundamentals. The weapon could get lighter, but not light enough to change its tactical role. But even as conventional machine guns reached their technological peak, militaries were already looking toward radical new firing mechanisms. The Heckler & Koch G11, developed through the 1980s and 1990s, represented the most ambitious attempt to revolutionize automatic weapons. Caseless ammunition eliminated brass cartridges entirely. Propellant bonded directly to the projectile in polymer blocks. The mechanical complexity was extraordinary. The promise was transformative weight savings and simplified logistics. Cook-off problems destroyed the concept. Residual heat ignited chambered rounds unpredictably. Humidity affected the polymer propellant. Temperature variations changed burn rates. Storage requirements became stricter than conventional ammunition. German reunification ended funding in 1990. The G11 never reached production. Decades of engineering produced a museum piece. Telescoped ammunition pursued similar goals through different methods. The LSAT and NGSW programs nested bullets inside cartridge cases rather than ahead of them. Weight savings reached 40% compared to conventional rounds. Manufacturing costs proved astronomical. Retooling production facilities required billions. Militaries rejected the economics. Electronic ignition systems replaced mechanical primers with electrical current. Reliability theoretically improved. Battery dependency became the new vulnerability. Soldiers now needed functioning electronics and power supplies to fire their weapons. The added complexity outweighed marginal gains. Metal Storm, an Australian concept, promised revolutionary fire rates through superposed loads and electronic ignition. Multiple projectiles stacked in a single barrel. Electrical pulses fired them in sequence. Claims reached 1 million rounds per minute. The physics made sustained fire impossible. The company declared bankruptcy in 2012. The concept remained a curiosity. Gas-operated and recoil-operated mechanisms still dominate. Belt-fed systems remain standard. Full-power rifle calibers continue service despite repeated attempts to replace them. Innovation stalls against fundamental constraints. Ammunition must remain interoperable across allied forces. Training costs escalate with new systems. Logistics networks cannot support frequent caliber changes. Suppressive fire doctrine remains unchanged. A century and a half after Gatling's hand crank, the machine gun remains what it always was, a compromise between firepower, weight, reliability, and the immutable physics of sending metal downrange at lethal velocities.